In this talk, I just want to recap what we know about deformation and smoothings of Toric Fano varieties and Toric singularities. So this talk is based on collaborations with different subsets of the following people. So Corti, Felten, Filip, Helge, Kaloghiros, and Ruddat. And I will mention these people along my talk. Okay. So I just want to start by saying what is the Fano search project, and probably also what is a part of 3CinG, which is basically a mirror symmetric correspondence between Fano manifolds, so smooth Fano varieties of dimension n, or maybe Fano varieties with terminal singularities, and on the other hand, this kind of special Laurent polynomials. So these are polynomials which are Laurent. So these are based on, it's a linear combination of some monomials with integer integral exponents, and then these are special in some way. And I will try to clarify a bit better what they are. And the correspondence works as follows. So basically you start from a Laurent polynomial, which has some good properties, and then you construct the Newton polytope of F, and then the Toric variety associated to that, and then a smoothing of that Toric variety. So associated to F, a smoothing of X newt F, and this X newt F is the possibly singular Toric Fano variety associated to the phase fan of the Newton polytope. Of F. So the Newton polytope is just the convex hull of the points in the lattice which appear as monomials in F. And then this is, if this Laurent polynomial is good, basically the origin is inside the polytope, and then you can create from the origin the cones over the facets or the faces of F. So this is also called this spanning fan, is the same thing. So this polytope is not the moment polytope, is not the polytope which gives a polarization of the Toric variety, because this polytope lives in the same lattice of the fan. So it lives in the co-character lattice. Okay, and then a natural question is, before saying this, and then the correspondence is up to a kind of, equivalence relations on both sides. So on one side, I consider Fano manifolds up to deformations. And on the other side, up to mutation. And a mutation is, I will not define it here, but it has a long history, and people studied mutations from very many different perspectives, so particularly cluster algebra people, I would say. And the mutation is just a birational transformation of the torus, and so a Laurent polynomial is transformed into another rational function of the torus, and sometimes this rational function is still a Laurent polynomial, so a regular function of the torus. And sometimes it's not. And then this is the meaning of when Laurent polynomial supports a mutation or not. Okay, and then basically there are two natural questions. The first one is, what are these special Laurent polynomials? What are exactly the mirror of Fano manifolds? And the second one is, how is it possible that the choice of a Laurent polynomial induces a smoothing of a Toric variety? And a priori, this is interesting. You could have two different Laurent polynomials with the same Newton polytope, So the same toric Fano variety, the same possibly singular toric variety, but then the choice of two different Laurent polynomials selects two different smoothings. Okay, and basically this is the aim of this talk, basically. Okay. So from this, it is obvious that we have to study the formations of toric Fano varieties. So let's look at toric Fano varieties a bit closer. So we started from a Fano polytope. P is a Fano polytope, and what is a Fano polytope? So it's a polytope in N. Maybe I should write something. So this is in N. The dimension of P is equal to the rank of N. So it's a full dimension. The origin is in the interior of P. And then every vertex of P is a primitive lattice point. And out of this situation, then you can create the phase fan of P, also called spanning fan, which is the cone over the facets. And then you create XP, which is the toric Fano variety associated to this fan. I mean, the toric variety, and then from this construction, you know that this toric variety is Fano. And of course, you can, as usual in toric geometry, this toric variety is obtained by gluing the affine charts, the affine patches. And so UF here is the affine toric variety associated to the cone over F, because and apex the origin. So you have your facet, you take the origin, and then you create the cone over that facet, and this is a cone, and then you take the toric affine variety associated to that, which is called UF. And basically now we have that XP is obtained by as the union of the UF. And so if we want to study deformations of XP, I would say that there are two steps. The first one is first to understand what are the deformations of UF. So need to study deformations of toric affine varieties of UF associated to the facets F of P. And the second step is need to glue these local deformations, so deformations of the affine charts, to get a global deformation of the toric Fano variety XP. So basically, these are the two steps in which I divide basically this, this subject. Any questions so far? Okay, I assume no. And here I just want to write a diagram which summarizes the situation for these kind of things. So I will stick to the case of Gorenstein, toric, affine, or Fano threefolds. Because for surfaces, I didn't say that, but the situation is much simpler. Because basically, if you have a toric surface singularity, the deformations, there could be many deformations. But if you stick to the Q-Gorenstein deformations, there is only one way to do that. In other words, Q-Gorenstein deformations of surface singularities, toric surface singularities, are unobstructed. And then there is another result which says that for the Petracci surfaces, there are no local to global obstructions. So in other words, every deformation that you create locally of the singular points can be glued and globalized to make deformations of the of the surface. So somehow the deformation theory is completely trivial because everything is unobstructed. And also you can see that from the combinatorial point of view, because there is only one choice of a special Laurent polynomial, which is basically given by giving coefficients 1 at the vertices of P and then on the edges of P, which is a polygon, you write binomial coefficients. Okay, for threefolds, the situation is much different and much more complicated. And so I will stick to the case of threefolds and Gorenstein. Probably many of these things that I will say in a minute holds also without the Gorenstein assumption and only Q-Gorenstein assumption, and maybe some of them will hold also for fourfolds or any dimension. Okay, and this table summarizes basically the current situation where the columns are the methods. And the first method is to study Minkowski decompositions. And the second method is zero mutable polynomials. And this is more general. Than the first one. Okay, and then on the rows, I have the setting, basically the affine setting or the Fano setting. Okay, so I just start from this block of this table. So here we want to understand what are deformations of toric affine varieties. And then here there is a crucial observation made by Altman in the 90s. And he observed that if you have a Minkowski decomposition of F, remember that now we are in the affine case, then this induces a deformation on the corresponding Gorenstein-Toric affine variety. And this works in any dimension, in completely generality. So this is very general. Okay, and starting from this, in the Gorenstein threefold case, in a joint project with Alessio Corti and Paul Hackin, basically we construct a smoothing of a Gorenstein-Toric Fano threefold, assuming that each facet of our polytope has a Minkowski decomposition where the Minkowski summands are of particular type. So they are A triangles. And here by A triangles, I mean either a unit segment or a triangle like this or a triangle like this. And then I always increase the lattice length of one edge, but the other lengths are still one. So basically, our theorem in this case is if you have a Gorenstein-Toric Fano threefold, such that the polytope has each facet of the polytope has Minkowski decomposition into A triangles, and then there is a technical condition that I will not talk about, then we get a smoothing, so a deformation to a smooth Fano variety. This result is depends on the fact that we are in dimension 3 and also uses this special kind of summands. And these triangles are very special somehow, and these are related to the compound Duval singularities.
Can I ask, how many of the Fano threefolds that are smooth are you getting by doing this? So how many will degenerate to something that looks like this?
I think I have everything which is possible, in the sense that out of 105, I guess 98 have a very ample anti-canonical bundle, and I think
okay, so that's
all of them.
Cool.
But of course, this doesn't apply to every Gorenstein-Toric Fano threefold, because sometimes you have a facet which cannot be decomposed into these things. Okay, any more questions?
Have you thought of fourfolds, like how many smooth fourfolds you get? I mean, I guess you have a similar A triangle equivalent for higher dimension, no?
Yes, but here there is a result of threefolds that we cannot avoid, which is, which is the result due to Namikawa, which says that if you have a Gorenstein Fano, so a Fano threefold with Gorenstein terminal singularities, this is mutable. So in other words, a Fano threefold with ordinary double points is smoothable. And so this is a result of Namikawa and is not related to Toric geometry, but we use this result in this kind of procedure here. And we don't have that theorem in fourfolds. Also because for fourfolds, there are examples of terminal singularities, Gorenstein terminal fourfold singularities, which cannot be smoothed.
Okay, thank you.
Okay. Any more questions? Okay. So far, I more or less talked about the first column. So suppose that you have a Minkowski decomposition of a facet, then you get Altman's theory for affine things, and then we have the second step, the global step, which is done in this case, assuming that the summands are of this particular type. And so this works for Gorenstein threefolds and assuming that the summands of this type. The problem is that this approach is not enough to consider all the Gorenstein Toric Fano threefolds, for instance, and also it doesn't apply to higher dimension. And so basically, together with Alessio Corti and Matej Filip, we started developing a conjectural picture for the deformations of a Toric affine variety, Gorenstein threefold, without assuming that the singularity, for instance, is isolated, or assuming also that you don't have any Minkowski decomposition. And this is what I want to talk about. And so then basically we conjecture that the smoothing components here are not related to Minkowski decompositions, but they're related to certain polynomials supported on that facet. So I will try to explain that a bit. If you're interested in that, you can look on the archive. This has already appeared, the conjectural framework. Otherwise, you can look at the talk by Alessio in Zag from, I don't know, a month ago. And this is just the conjectural picture. And basically using a kind of Gross-Siebert ideas, together with Alessio, Simon Felten, and Helge Ruddat, we are trying to basically to prove that this conjecture, or at least to construct a smoothing starting from a Laurent polynomial. And this method, as usual in Gross-Siebert program, uses degeneration and then put in some log structures. And I want to talk about this at the end of my talk. And then we hope, with the same group of people, we hope that this method can be globalized to treat Fano threefolds. And this is a method which is more general than the previous column, and probably, hopefully, can be generalized more easily to fourfolds or to higher dimensions. Okay, the last thing I want to say about describing the situation is this other work that I've done together with Anne-Sophie Kaloghiros. And basically, using the first column and Altman's theory, we constructed examples of obstructed K-polystable Toric Fano varieties. And so this gives the first examples of points in the K-moduli stacks and K-moduli spaces, which are singular. So these are the K-moduli stacks and K-moduli spaces have been recently constructed. These are probably the correct way of studying moduli of Fanos. The origin comes from Cayley-Ranstam matrix, and our example, so the power of Toric geometry is that we can run the computations completely explicitly, and then we can really understand very precisely what are the local structures of these stacks and moduli at the Toric points. And in this way, we can find points where the stack or the good moduli space is not unibranched or non-reduced. Okay, any more questions about this before so now the plan is that talk briefly about Altman. So what are Minkowski decompositions and deformations? I completely omit this part here, and then I will talk about this. And for the fourth part, maybe Helge will say something in his lectures. Okay, any questions at this point? Okay, so I will go on and talk about this Altman's theory. So Klaus Altman made this fundamental observation in the 90s, I would say, which says that if you have a lattice polytope, this induces a Gorenstein-Toric singularity, and then if you have a Minkowski decomposition of this polytope, then you have a deformation of the corresponding Toric affine variety. So let's make an example. So you take the Del Pezzo surface of degree 6. So this is P2 blown up in 3 points. This is a Toric surface, and its anticanonical linear system is very ample. So you can embed it inside P6, and then you take the affine cone over that. And so this is a surface, so the cone is a threefold, and since this is smooth, this cone has an isolated singularity at the vertex of this cone. So maybe let's write in this way. Let's call it U. Okay, now if I interpret this, so this is a Toric affine threefold with an isolated singularity. Okay, so if I want to interpret this in Toric geometry, basically this threefold is associated to this lattice polygon. So you consider this lattice hexagon, which is a polygon. Then so this is inside the Z2 lattice of rank 2. Then you place this lattice at height 1 in a 3-dimensional lattice, and then there is I hope you can see my face. There is the origin below the hexagon, and then you create the cone over that. And then U is the Toric variety associated to this cone. And this hexagon has 2 Minkowski decompositions, 2 maximal Minkowski decompositions. One is this one, and the other is this one. So if you are not familiar with Minkowski decompositions or Minkowski sums, you should think that you pick any point in the first triangle, you pick at any point in the second triangle, and you take the sum. And this procedure basically makes, you start from the first triangle, and then to each point of the first triangle, you attach the second triangle. And then you understand more or less what happens when you move the red triangle going around the first triangle. And then you see that basically you get this hexagon. And the same works for the segments. So now I will delete this horrible picture. Okay. And these 2 Minkowski decompositions give different smoothings of U. Okay, and this is basically the end of the story. But I want to make a further step, and I want to talk about Laurent polynomials on this on this situation. And what I do is the following. Now I consider this Laurent polynomial. So in other words, I consider a Laurent polynomial with this triangle as Newton polytope, and then I consider this point gives a monomial, and then I consider coefficient 1. Then here this point gives a monomial, I consider coefficient 1, the same here. So basically this is, if this is the origin, this polynomial is just 1 plus x plus xy. And the second polynomial here is 1 plus xy plus y, I would say. And then basically the Minkowski sum is just the Newton polytope of the product. And if you consider this product, then you will discover that you get this polynomial. Yes. So basically the coefficient of the interior point is just 3. This is because you can multiply, I mean, there are 3 ways you can take a monomial here and the monomial here such that you get the center of this hexagon. And if you do the same, yeah?
Oh, sorry, can I ask a very basic question? So the fact that the Minkowski sum of these triangles correspond to the product of these Laurent polynomials, is this a definition or it's a property?
I would say it's a property. Okay. So in general, so aside, if you have f and g Laurent polynomial, then the Newton polytope of f times g is the Minkowski sum of them.
Okay, thanks.
Okay, and now if I consider the other situation, basically I get 1 plus x times 1 plus y times 1 plus xy. And of course here up to translation because I'm lazy. And then in this case, I get this situation. So the vertices have still coefficients 1, and then in the middle I have coefficient 2. So I could say, so Altman's theory says that these 2 smoothings of U corresponds to these Minkowski decompositions, but using this trick, I can say, okay, but these 2 smoothings of U correspond to these 2 Laurent polynomials, which are basically the same with the difference of the coefficient of the interior point. Okay, and now the last sentence is, but Altman's technology is not enough to treat all Gorenstein-Toric Fano threefolds, and now I see the following example. So this example, I think, is originally due to Stevens, and then it was elaborated a bit better by Brown, Reed, and Stevens in an attempt also to consider codimension 4, Tom and Jerry, these kind of things. So the example is the following. You take P123. This is a weighted projective space. It's a Toric Delpezzo surface with 2 singularities. One is an A1 point and one is an A2 point. So this is a singular Delpezzo surface of degree 6. You take the anti-canonical embedding, which embeds inside P6, and then you take the cone over that. And then I consider U this cone. Now, this is not an isolated singularity because the surface was singular. So basically, U has 2 curves along which is singular. Another description of this threefold, this is an affine threefold, is the following, is 1, 6, 1, 2, 3. And by this, I mean a quotient singularity of this type. So basically, you are considering the 3-dimensional affine space with an action, a linear action of the cyclic group of order 6 with weights 1, 2, and 3. And then the quotient is this singularity. This is a quotient singularity. And another description of this variety is from Toric geometry, and works as follows. You consider this triangle. So this point here is the point, so this is the origin. And I hope you can see the red dot. And this point here is -1, -1. This point is 2, -1. And this point is -1, 1. So this is a triangle inside the lattice, a two-dimensional lattice. Now you put this lattice at height 1, and you create the cone over that. So basically, this point becomes the point -1, -1, 1. This point becomes 2, -1, 1. And this point becomes -1, 1, 1. And now you have the cone over this triangle, and this is, I call it sigma. This is a cone inside the three-dimensional lattice, and U is the toric variety associated to sigma. Okay, and basically there is a perfect correspondence between the edges of this triangle, which I call E1, E2, and E3. Notice that the length of E1 is 1, the length of E2 is 2, and the length of E3 is 3. And there is a correspondence between edges of this triangle and two-dimensional subcones of sigma, and equivalently to using the toric orbit cone correspondence with the one-dimensional toric strata of U. So basically, these are the curves. And since here the lattice length of E2 is 2, this means that along this curve, U has generically transverse A1 singularity. And the same works for C3, and here you have A2. So basically, there are two curves, which are the singular locus. So the singular locus of U is just the union of these two curves. And they meet at the zero stratum, where the singularity is worse than being compound duval. So it is this quotient singularity. And then it was observed by Stevens that this singularity as a versatile deformation with two irreducible components. And these two irreducible components in this conjectural picture that we made together with Alessio Corti and Matej Filip, these two components correspond to the following two Laurent polynomials, which are zero mutable. And I will say in a bit what I mean. And the polynomials are these ones. So I always give binomial coefficients to the edges, and then in the middle I write 2 or 3. So I call it F2 this polynomial and F3 this polynomial. Okay, and so this is an instance of a more general picture which probably works. I mean, we hope that it works. We conjecture it holds for every Gorenstein toric affine threefolds. Okay, let's be a bit more precise about the situation. So I have F, a lattice polygon, sigma, the cone over F placed at height 1. So this is F inside Z2, and then sigma is the cone over F times 1 inside Z2 plus Z. So this is my N. And then sigma dual is the dual cone, and U is the toric affine variety associated to sigma. So F in the previous example, F is this triangle here. Okay, and then U is Gorenstein because there is a special element which I denoted by U, which is 0, 1, and this is the Gorenstein degree, which is basically, I mean, the point 0, 0, 1. And delta U is the toric boundary of U. This is the reduced sum of the toric prime divisors of U, and in this case, it is a Cartier divisor. So it's given by the function, the vanishing of the function associated to U. In the situation of my example, basically I find that sigma dual inside the dual lattice is generated by the following three rays, Z1, which is this ray, Z2, and Z3, which are basically orthogonal to the edges E1, E2, and E3. And here, this is just a picture of a slice of sigma dual. So basically here you find Z2, Z3, and Z1. So these are the rays of sigma dual, and then in the middle there is U. And one can show that actually these lattice points, which I call U, W, V1, and V2, they are generators for the monoid sigma dual intercept M. And so basically this means that they can be used as coordinates for our variety. So in other words, what we get is that U is embedded inside A7. So where, I mean, these points are 7. 1, 2, 3, 4, 5, 6, 7. And so this is a codimension for Goldstein variety. And I mean, a lot of mice studied this very closely. And there are 9 equations, if I remember correctly. And these equations can be written in basically 2 ways, which Miles calls Tom and Jerry. And from the way you write the 2 ways you write these equations, then it is not difficult to write down what are the deformations, the 2 deformations of your equation, your variety. So the deformation respect only one type of the equation you choose. Okay. Any questions so far? Okay, now I just want to say something about the conjecture done with Alessio and Matej. So as before, F is a lattice polygon and U is a Goldstein-Toric affine threefold associated to the cone over F placed at height 1. And what we conjecture that there is a natural bijection between 0 mutable polynomials with Newton polytope F and smoothing components in the deformation space of the pair U with the toric boundary. So maybe I should say something about these 2 sets. The first set, so we are considering F, the polygon, and then we are considering basically polynomials with binomial coefficients on the boundary of F, and then we have to understand what happens inside F. And we have a recipe for doing that. And this is just finitely many of Laurent polynomials. So they have all integer coefficients, I would say non-negative integer coefficients. And these special polynomials correspond to having mutations and this kind of stuff. Unfortunately, I don't have time to talk more about this. But you should think that these are nice combinatorial objects on a polygon, and which can be easily described. And this is related to mutations. Of course, there is also a classical surface theory on this. So they are just some kind of sections of line bundles on certain blow-ups of toric surfaces. On the other side, here I have smoothing components on this. So here I consider U together with the boundary, and then I consider deformations of the pair. Actually, there is not much difference in considering deformation of the pair or deformations of U itself. The reason is because U is affine, and this is a Cartier divisor. So basically, there is the map that forgets the boundary is smooth. So actually, these 2 spaces are the same. So this is closely related to def U. So, and this map is smooth. So they have the same reducible components, for instance. And then I call MF the associated smoothing components of F. And then we also conjecture that this MF is smooth. We already know that it's generically smooth because since it is a smoothing component, it means that at the general point, it is unobstructed. And the third thing is probably one of the most important, and says the following. So somehow the tangent space of MF, the component at the origin, This is a subspace of the tangent space of this guy, of this germ. And it is a representation of the big torus acting on you, because everything here has a natural action of the torus. So in particular, is a vector space with the torus action. So it is a sum of reducible representations which corresponds to characters of the torus. So basically elements of M. And we have a complete description of what they are, the characters involved, and what are the multiplicities of these characters. So, these weights appearing in this representation are basically determined by the mutations of the Laurent polynomial f, which can be done to f. So basically, you consider all the mutations that you can apply to f, and then this gives the characters of this representation. Maybe I should go back to these two Laurent polynomials. And I just want to mention the difference, one difference between these two Laurent polynomials. One difference is, for instance, here, the fact that in this polynomial, here I have 2 and 2. So this means that this line here is divisible by 1 plus x. And so this means that I can create a mutation where this line is negative at height -1, and this line is at height -2, for instance. But I cannot do this here, because here I have 2 plus 3x, and this is not divisible by 1 plus x. So this means that there is a mutation which can be applied to F2, but not to F3. And the same works also in the vertical direction, because here, for instance, this line here is not divisible by 1 plus y, because I have 3 plus 2y, but here, yes, because I have 3 plus 3y. So this kind of difference of the mutations which can be applied to different Laurent polynomials. Okay, now I want to briefly say something about the deformations of the pair U with the boundary. And here I basically wrote down the pictures of 3 plane slices of sigma dual embedding in the 3-dimensional lattice. So basically, I remember that my F had 3 edges, E1, E2, and E3, and now I'm considering the orthogonal of these edges, and these are planes. So here I have E1 perp, E2 perp, and E3 perp. And basically, these pictures are just the pictures of these 3 planes. And the shaded area here, so this area here, is just sigma dual, the cone sigma dual. And remember that there was the point U, which was the Gorenstein degree inside. And then there were Z2, Z3, and Z1, and also other lattice points. Okay. And now I consider basically, let's start from the yellow situation. I consider the point -U, and then I go down by 2 because E2 has lattice length 2, and then I consider this basically infinite strip in this way. Then here I consider this is the origin. I go down by 3 because the lattice length of E3 is 3, and then I consider this infinite strip, the green one. And then the blue one, the similar one for E1. And then here I colored some dots of this. And actually, basically, the degrees of this representation, which is the tangent space of the deformation functor of U with the boundary, are exactly these colored dots. So the red, the yellow, the green, and the blue. And one can write down the equations for the embedding of the germ of the deformations of the pair inside the T1. And the equations are simply S1 alpha times S1 beta equal S1 alpha times S2 gamma equals 0. Here, notice that I have 3 of these dots, I have given name to them. Okay. And so basically now I have two irreducible components. One is S1 alpha equals 0, and one is S1 beta equal S2 gamma equals 0. So these are the two components of the smoothing, and this is related to F2, and I think this is a Tom, and this is related to F3, and this is a Jerry. Okay, so this is basically the conjecture picture. Now I want to sketch briefly a way to prove this kind of things. So the strategy to construct a smoothing of U is, first, you degenerate U to a reducible reduced U0 by centrally subdivide sigma dual. This is basically the Mumford degeneration or Grebner degeneration. Then the choice of a zero mutable Laurent polynomial induces a log structure on U0. Third, we construct a log crepant log resolution of U0, and this way Y is log smooth. And then fourth, we construct a smoothing of Y, and then we push it down to U0 and to U. So this is basically the idea. And I think probably Helge will say something about 3 and 4, or maybe only 4. And I talk about 1 and 2 now. So the step one is we centrally subdivide sigma dual. So inside the sigma dual, there is this half line, which is the line generated by U, which is the special Gorenstein degree. And then here inside is here. And then we subdivide by using this. So now if I consider a slice given by the previous situation, basically I get now three-dimensional cones, which corresponds to the cones over these three areas. So basically I join Z1 with U, Z2 with U, and Z3 with U. So this gives a fan with support sigma dual. And now I can create the Stanley-Reisner scheme associated with this fan, and some people call it Toric bouquet. And this is U0, and U0 is a degeneration of U. And since there are three maximal cones in this fan, U0 has three irreducible components. So for instance, in this case, I have this cone here corresponds to A3. This cone here corresponds to this compound Duval singularity, and the same works here. And then these two threefolds intersect along a surface, which is associated to this blue line, blue segment. And this is a smooth surface. And then there is a green smooth surface and the yellow smooth surface. So this is the picture of U0. So it's a kind of, so U0 is a toroidal crossing space. So it's not normal crossing, but not too far. Okay, and the second step is that the choice of a zero mutable polynomial, you consider the mutations of this Laurent polynomial, and out of that, it is possible to construct functions on the, here I made a mistake, not on the double locus of U0, but on the components of the double locus. Of U0. So basically I have my U0, which is given by the union of three threefolds. And now I'm considering functions on the blue surface, on the yellow surface, and on the green surface. And these functions are exactly, basically, the degrees of the T1. More or less. And these functions are given as follows. So for instance, here I consider both the two situations. So I consider either we are in the choice of F3 and then I impose this equation, or I consider F2 and with this equation. Okay, and the functions are given as follows. So I will try to be quick. So notice on the red lines, I just use 1 and S0 to the correct power. No, here there is no 3. And so basically this means that this guy here is u plus S0 square, of course up to translation. And this guy here is just u plus S0 cube. Okay, and now here I write S1 epsilon, 2 S1 epsilon S0 plus S1 beta, and then S0 S1 beta plus S1 epsilon S0, and here S2 beta S0 plus S2 gamma, S2 beta plus S2 epsilon S0, and then S2 epsilon. So these are the coefficients of some of these dots. And then here, when I don't write any coefficients, means that it's completely free and it's completely arbitrary. And also here is completely arbitrary. And now we see, for instance, that if we are in this regime, so S1 alpha, before saying that, when I consider these functions and I restrict to do the triple locus, which is this line, they satisfy the Gross-Seibert joint compatibility condition at codimension 2 joints. Because exactly I have here what u plus S0 square, u plus S0 cube, and here I have u plus S0. But notice that here I have more conditions, not only the Gross-Seibert condition. Indeed, if I have S1 alpha equals 0, this means that this guy here is divisible by u plus S0. So let's make it blue. So this part here is divisible by u plus S0 if S1 alpha is equal to 0, because S1 alpha vanishes. And the same works here, because now assume that you are in this regime where S1 beta is equal to S2 gamma equals 0, then this means that this is a square, because this vanishes and also this vanishes. And the same works here. So in other words, this and this divisible by u plus S0 square, and then this is divisible by u plus S0 if we are in this regime. And so now, if I consider the 0 locus of these functions, this means that there are curves which are not smooth anymore, because I have this divisibility on translates of this. So the fact that here I have a cube means that the curve has multiplicity 3 when I intersect with this line, but the fact that I have here a divisibility along u plus S0 square or u plus 0 means that this curve is also singular at this point. So basically, if I consider the log singular locus, which is the regions where the 0 locus of these functions, these are curves inside the double locus, then these curves can be singular. So for instance, if I take F2, here I have a curve with a node at this point. And if I have F3, I think I get a curve with 3 branches on this green surface. And so these singularities of the log structure are completely out of the classical Gross-Seibert program. And so they require to be analyzed, and the idea is basically to construct a log graph and log resolution, which basically make the singularities of the log structure disappear and try to smooth that and then push it down. And probably Helge will say something about this. So, so I'm done, and I should ask if there are questions.
Okay, so I have 30 minutes. I'll try to add to what Andrea spoke about, first by repeating a result that got proved last year jointly with Simon Felten and Matej Filip, names that you've seen already. And I need to find my, okay. So let me repeat what got proved. So that's something that's not contractual, it's already published on the archive. So if X is a proper normal crossing variety, with some rather mild conditions, so you need some form of Calabi-owness, so effective anti-canonical class, so log Calabi-Yau, effective anti-canonical. And then you want some sort of positivity in the infinitesimal deformations. So the T1 sheaf is defined as the first X sheaf of the ordinary deforms with the structure sheaf. So that's known to singularity theory people. It's just the T1 sheaf classifies infinitesimal deformations. And this sheaf is supposed to be generated by global sections, some kind of positivity property generated by global sections. And then we want the singular locus of the normal crossing space to be projective. Of course, you can ask the entire space to be projective. I've asked the entire space to be proper, almost projective, but a bit pedantic what we really need. Because there might be situations where you want to weaken things a little bit. So if that all holds true, then we prove in this theorem that X is smoothable, which means that there is a flat family, a one parameter family in the analytic category. So over a holomorphic disk, and the nearby fiber is a manifold. Okay, so that's a nice way. You can smooth these normal crossing spaces if you have these conditions. Very nice. And let me quickly tell you the proof strategy and then explain why it doesn't apply on the nose in the situations that Andrea told you about. So first, let me say how roughly the strategy of the proof works. The first step is you put a singular log structure on X. So I don't want to go into what a log structure is or anything. If you don't know what it is, just think of it as some magic powder that you can put on there. But this magic powder has a particular local shape. So that's the main point here. We're sort of restricted in what we can handle in terms of the log singularities that is locally given by the classical thing. If you are an algebraic geometer and you think of something with log, a log space or something, you think of a variety with a Cartier divisor or wave divisor, okay? So that is indeed a log space. And many log spaces, maybe all, are given in that way, locally by a pair, and then can restrict the log structure to subspaces. So we want our single log structure to be locally given by a pair, that's V comma divisor, so variety, it's an affine variety with a divisor, and here V is an affine toric variety, and D is a toric divisor in the toric. Okay, so among all possible pairs, this is quite a restriction, of course, because affine toric varieties are special varieties, and then toric divisors inside of those are also special. Nonetheless, that's quite powerful still to have log structures of this shape. For instance, they need not be log smooth. So if you look in the classical literature on log geometry, most of the time people assume log smoothness. If you have the setting where you have an affine toric variety with a toric divisor, it's not necessarily the entire toric boundary. You don't end up with log smoothness. So this is more general than what you find in the literature. And models like that were already used before by Marcos and Bernd Siebert. So we built on their work and we put a log structure on the space X. And the novel idea here is that you can do this by having a section of this T1 sheaf. Okay, so we connect this T1 sheaf with the usable log structures. That's also not entirely new. That connection had also been done by other people before. but we made it more precise and conceptual. And then we use the assumptions that are given in this theorem to produce a block structure that has these local models. Okay, that's the first step. And then the second step is essentially the thesis of Simon Felten. So first you consider differential forms. Let's going to find differential forms on the space. So we have now X with this single log structure. The log structure has a locus where it's log smooth. Okay, so let me denote U to be the locus where it's log smooth. The complement has codimension 2, which is a good condition. So this is the smooth locus. So smooth in the sense of log smooth. Okay, so it's much bigger than the ordinary smooth locus. Log smooth. And then you define the differential forms. That notation we use W for that. So basically introduced by Simon in his thesis. So you just use the push forward of the log differential forms on the smooth locus. Okay, so these are the log differentials on U. Okay, and I'm suppressing in my notation that everything is done over the standard log point. If you know log geometry a little bit, the log structure has a map down to a standard log point. I'm completely suppressing that from the notation. Everything's relative over the standard log point, but let's not go into that. So I just use this notation. So you take the push forward of differential forms from the smooth locus, and that's what you use for differential forms. And then you want to prove that there's a Hochschild-Round degeneration. Okay, that's the main part of the step. Prove a Hochschild-Round degeneration. That means you know there's this usual Hodge theory spectral sequence where the one term looks like you have the usual Hodge groups, HPQ, and then it's as a spectral sequence, it always degenerates to hypercohomology P plus Q of the space with complex. So I should use W here. Okay, and you want that to degenerate 81. Okay, so that's what usually happens if you have Hodge theory going on and things work in the way they should, then that degenerates 81. So that's something you want to prove. And once you have that, that's a key ingredient for the next step. And it's the final step. You use a log extension of Bogomolov-Toric theory. So that's, you know, Bogomolov-Toric theorem is that Kaloghiros have unobstructed deformations. And we have this assumption here that the anticanonical is effective, so log Kaloghiros is good enough for that theorem. But we use another log version, not just that, you know, the canonical class may have sections, anticanonical class may have sections, but also log in the sense of log geometry that we've been doing with log structures. So that's not an entirely trivial step, but there exists an extension to the log geometry from this for this Bogomolov-Toric theorem, and that was done by Chan-Leung Ma. Very recently, Chan-Leung Ma, in their work that has the title Geometry of the Maurer-Cartan Equation. Geometry of the Maurer-Cartan. And so on. So the title is a little longer, but that's the final step. Okay, so roughly the proof strategy works in these three steps. You first put a log structure on the space, then you prove a Hochschild-Round degeneration for the differential forms that are the push forward of the differential forms to the smooth locus, and then you apply Bogomolov-Toric theory, Chan-Leung Ma. Okay, that's roughly how it goes. That has been done in this theorem. So, okay, the theorem that we have is proved that way. It works. But now we want to do something else. We want to do more than that theorem. We want to prove other theorems. So the goal, which we might have gotten from Andrea's talk already, the goal is to apply the similar strategy in the situation that worked for Fano. Okay, apply similar techniques to smooth Toric Fano varieties. So they may even be affine. So the interesting thing is there's even issue in the affine case that you've learned. So the final goals are, maybe I can give you 3 dots of what should be achieved. One is to prove the conjecture that we just learned about by Petracci, Filip, and Corti. We got the order wrong. So that's one thing, because this is about an affine toric variety which has non-isolated singularities, and the conjecture says that the smoothing components of that, in the deformation space of it, that they match up with zero mutable polynomial mutation classes. Okay, so that's a conjecture. That's one thing you might want to prove with smoothing technology, as I sketch here. Then there's the classification of Q-Gorenstein Fano threefolds. Okay. So we all know the classification of smooth Fano threefolds. I think there are 105 of them, plus or minus. And you know, you might care about not just smooth ones, but Q-Gorenstein Fano threefolds. And that's something that may well be tractable by what I'm going to tell you about today. I believe we're getting there. It's not far away from that. But then somewhat more ambitious is to classify smooth Fano fourfolds. And in principle, the techniques I'm going to present today are independent of dimension. Okay, so the only thing that you need the dimension for is to construct Kreppner solutions. Okay, that's kind of not so hard in dimension 3, I would say. In dimension 4, it's a little harder, so that something gets a bit done here. But apart from that, all the techniques I present here today are independent of dimension and working on dimension. Okay, smooth, so there's classification. So these are kind of the motivating goals, and now I'm going to tell you what is the main obstacle, the main problem in doing that. So we have this theorem that you see on the left. Why doesn't it apply right away? And now the main point is for the applications. The log singularities are way more severe, okay? Way more severe. So in particular, they're no longer permit toric models. Permit toric local models. It's even funnier, you know, we don't even know local models. We don't even have them. So the affine case is a challenge. We don't have locally a deformation of it. It doesn't exist yet. So that's something that should come out of the work now. Okay, so it's kind of interesting. We don't even have local models. We don't know what it locally total space of the deformation would look like. So for those kind of singularities, Andrea gave you a lot of input. So I would like to refer to here. See Petracci's talk. Okay, so what's the key idea to overcome this obstacle? Okay, the key idea was already mentioned by Andrea. I'm going to repeat it. So replace A, what we had, X was locally, in the previous theorem, locally given by the pair of an affine toric variety V, D. In terms of the singularities of the log structure, they're given by that pair that no longer works. But now we have something else that we can use, and we use that a lot. So X instead is locally again, with the local statements, locally given by, well, not given by, but it permits a local log smooth resolution. Okay, so this is log smooth and log rapid. Okay, so that's something we assume to have. And the reason we assume that is because in the cases we looked in these examples that Andrea talked about, that exists. Okay, so in Andrea's examples, you can produce that. I use that notation pi here. So that's something we use as a replacement for not having toric local models. Okay, all right. So here's a baby example. where both exist, okay? The case where both A and B exist. And that's a famous example. I didn't invent it. It was talked about long before. It's the market Bernd. You know this very well. So it's the threefold, the total space, the local model is a threefold. It's a spectrum of the ring with 4 variables in one relation. And the relation is xy equals tw. So this is, you can recognize as a conifold. It's a threefold, the toric threefold, with a one isolated conifold singularity. And I consider a map down to the affine line from here, given by the variable t. And then I'm considering my space x to be the 0 set of t. Okay. So that's an affine toric variety. The toric boundary consists of 4 surfaces, 4 A2s, and the 0 set of t consists of 2 of them. Okay. So as a picture, you see it down here. So the left, you know, this picture indicates 2 planes meeting in a line. That's what x looks like. And in terms of the previous notation, x is also equal to d. So the log structure I'm considering is the log structure arising from the pair v comma d. All right. So that's a log pair. V comma d is an example for what I talked about. And it is log singular in the origin. Okay, so that's the point x equals y equals t equals w equals 0. And where it's a 0, you can show it's log singular. Okay, so even though it's given by a toric variety and so on, it's singular at that point. And here I've given you a picture. So I said the toric boundary has 4 components, but only 2 of them are part of x, namely the component where t and x are both 0. That's one component of x, and then the other one is where t and y are 0. So I'm drawing here the space x, and it has this log singularity at the isolated point where both x and y and w are 0, and t is also 0. Okay, now this log singularity has a resolution, because what you can do is you can take the total space, you can take V, and make a small resolution of the conifold singularity by replacing the singularity with a P1. So that P1 then, depending on your choice of resolution, ends up in one of the 2 components of X. Okay. And here it's part of, I don't know, the component where Y is 0, and that would be my log smooth, log crappant resolution of the example. So it exists. Okay, this is the log smooth resolution. So one can check that actually indeed upstairs log smooth. It's also log crappant. Nice. Okay, so this is an example. This baby example is one where you have both happening. You have a toric local model, but you have also a log smooth, log crappant resolution. All right. Now, what am I going to do with that? There's a key observation that you want to make with this log crappant resolution. Namely, if I may call that x tilde maps down to x, the resolution is a homotopy equivalence. Homotopy equivalence on the Kato-Nakayama spaces. So this is again something that you maybe haven't heard about before. If you don't know what it is, just think of it as a topological model for the nearby fiber in a smoothing. Okay, so if this log space X has a smoothing, then there's a topological space you can functorially associate to the log space, which is homeomorphic to the smoothing. Okay, at least that has been proven in decent cases. But this topological space always exists for as bad log stores as you like. There always is this topological space, Kato-Nakayama space. And if you use this map pi, the log resolution, and study it at the level of these topological spaces that model the nearby fibers of the smoothing, then, you know, if the resolution gives the same smoothing as downstairs, you would expect those topological spaces to be more or less the same. And the notion here is homotopy equivalence. Katagama space has this homotopy equivalence, meaning more or less that the smoothings are more or less the same topologically. And you can study this explicitly in the simple example. So if you smooth the normal crossing space given by these two affine planes, then what happens is you replace all points by a point in the nearby fiber, except for the points that lie over the singular locus here. They become circles. But then if you look closely at the local model, so local model again is this, this total space here, the threefold. If you turn on t, say you put t to a small value or t to 1, then in fact you notice that at the log singular point, there's not a circle in the nearby fiber, there's only a point. Okay, so the pictures you have at the general points, you have just points in the nearby fiber. Along the singular locus, the generic points, you have circles in the nearby fiber, and then at the log singular point, there's still just a point in the nearby fiber. Okay, that's what it looks like. That's a Katagama space of X with log structure. If you do the same with the resolution you have this P1 that got inserted here. Now the log structure is smooth, so that means in the Katagama space you have circles everywhere in the double locus. There's all circles here. But then you have this new P1 or something happens, and what happens truly is here, you get over it, you get a disk that bounds the circle that lies where previous singularity was. Okay. So if you compare these two spaces, in one case you have a point at the log singular point, and the other thing you have a circle, but the circle is bounded by a disk. Okay, and it's not hard to see. Well, that's a homotopy equivalence. Okay, whether you have just a point or you place the point with a circle that you put a disk inside, that's just homotopically the same. All right. So that's important for us. So we want that our resolution has this property. Not all resolutions have that, but we want a resolution that has the property that it's homotopy equivalence on Katagama spaces. All right. And let me finish my presentation today with two useful facts about these topological models for the nearby fiber that exist even without an algebraic smoothing, those Katagama spaces. First of all, a nice theorem by Smale that's useful on when do you have a homotopy equivalence. Okay, let's now say we have a map, a surjection of topological spaces, and I want to specify exactly what all properties they should have. Say decent topological spaces, so continuous map of decent meaning is something like CW complexes that are locally contractible, blah blah blah. Okay, so decent topological spaces. Then you want it surjective and proper. Okay, so we have all that. And the key ingredient then is have contractible fibers. If pi has contractible fibers, then pi is a weak homotopy equivalence. Weak meaning you see it in all the K groups and so on, homotopy. So you basically cohomologically, it's all they have the same space. We'll go to equivalence. Okay, so that's super nice because you can easily check that, you know, whether the fibers are contractible. This is super easy to check. So that's super useful. The next thing that I want to finish with is a warning. Okay, so these log smooth resolutions, they exist in many cases, but they're not always having the property that they induce a homotopy equivalence on the Katagama space. And here's a counter example. So the warning is there are examples where homotopy equivalence fails. Namely, you can take a log conifold, okay, log conifold. And here I'd like to advertise a future paper with me and Siebert. So hopefully it's coming out this year or next year. So we work on log conifolds and prove stuff about them. So the simplest way to give one is you look at that local model. Okay, so you with that equation, if you send t to 1, then yes, you have a conifold, right? You see that on the nose. But if you send t to 0, we just have, again, two planes meeting, actually in two threefolds it's now, because the threefold family. So you have two affine three spaces meeting in a two space. If T is 0 and if T is non-zero, then you have a conifold. So this is a degeneration of a conifold. It's also a toric local model. So it's a log conifold with a log structure given in the toric local model. And this one has a resolution, Crepin resolution, but it doesn't have the property that it's a homotopy equivalence. Okay, so this resolution has resolution, but it's not homotopy equivalence. Why is that not? Well, because the resolution gives you the smoothing of the conifold, whereas the downstairs you have the singularity still existent. So there's a difference in the singularity and the resolution. What the resolution is. So upstairs you get the resolution nearby fiber. Downstairs you get the non-resolution. A different topologic. And there's yet another even simpler example. Take a baby example from above. And blow up somewhere else. Okay. So instead of blowing up in the log singularity, you just leave it as it is, sitting there, and blow up some other point. Okay. So I can blow up here. Or blow even up, I don't know, some point that's not in the double locus, whatever. And then you see that's not a homotopy equivalence. Okay. So blow up somewhere else. Elsewhere is not a homotopy equivalence. And of course, you can combine them. You can, resolve the log singularity and then blow up somewhere else, or blow up too much. You don't get a homotopy equivalence. Okay, so that's really a specific thing that you have this homotopy equivalence, and we believe we can prove it in all the cases that Andrea mentioned in his talk. Okay, so those ones have these resolutions with homotopy equivalence in the categorical space. All right, that's as much as I want to say now. I'm going to continue later with other stuff.